मुझे कुछ बोलना है क्या? हाँ, people are already there. Six people are watching. Okay. Okay. Hello, hello, viewers and students of our Introduction to Material Science and Engineering course. I'm happy to interact with you in this live session. So you can start your questions. We do have some of the questions which you have given in writing in advance, but maybe you can ask the questions. But we should know that the person who has asked the question is around. Okay. But we should at least see some hello or some response that there are people around. Or shall we start answering? If there is no response. What is the first question? Gate mechanical preparation. Yeah, there was a question by whom? Chinmay. By Chinmay regarding what part of our course is relevant for gate mechanical. I think all parts in our course should be relevant for a mechanical engineer. In fact, at IIT Delhi, this course is required for BTech in mechanical engineering, or for all students of graduating in BTech in mechanical engineering. So we have decided that the course content is required for mechanical engineers. I also feel that all good mechanical engineers should know at least this much of material science, which we do in this course. Because of your question, we did check the syllabus and we found that the syllabus mentions some particular, in fact, the first topic which the syllabus mentions in material science is actually whole of material science. It says structure and property relations for engineering materials. And that's what we do in this entire course. So that way the entire course is taken as the syllabus in that one phrase, structure property relations in engineering materials. That's the basic theme I have explained in the introduction also. That's the basic theme for this course. After that, some few specific topics have been mentioned, and they are, for example, they are heat treatment, phase diagrams. These are specific chapters. In fact, phase diagram chapter will start soon after the defect chapter. So that is the next chapter which we will be starting probably from next week. Next week it will be phase diagram, and that's one of the topics listed in mechanical engineering gate syllabus. After that, later we will do heat treatment. Stress strain relations for materials also is one of the course, and we will do that. So you will find quite a bit of things here which will be suitable for the materials syllabus of the mechanical engineering gate.
Get started getting some questions here.
Yeah.
Can I do MTech with this professor?
No, this first one is that is starting with Rajesh Roshan. Rajesh Roshan, good evening. So good evening, Rajesh Roshan. Nice to see you. Nice to see another person with my name. Mahip Kumar Upadhyay. Good afternoon. Shaikh Ismail, good evening. Pratap Sharma, good evening. Pratap Sharma has a question also, I think he has given. I remember. And Shaikh Ismail, I'm much impressed with your teaching. Thank you very much. I'm also much impressed with your commitment, trying to do a full course of 12 weeks. Not easy, particularly when there are other courses available with less time, commitment. Sir, can I do MTech in this subject as I am from mechanical? I think MTech in materials engineering is possible with mechanical engineering background in most cases. In in most institutes, materials engineering program, MTech program will accept mechanical engineering student. We are also starting, so you can apply for IIT Delhi also. We are also starting materials engineering program from this July. This will be a new materials engineering MTech program. And we also, for our program also, mechanical engineers do qualify.
Why do we choose only a single set of direction, even though there are direction of both set of
Amrit. So Amrit is asking an interesting question, but we have not yet reached there. So this is a little bit in advance because we have not yet started plastic deformation discussion. So the question is, why do we choose only a single set of direction when both positive and negative nature of the slip plane is possible? In fact, on a given direction, slip is happening in both positive and negative side. Because when slip is happening, one part of the crystal is slipping in the positive sense of the direction, and another part of the crystal is moving in the negative sense of the direction. So actually slip is happening in both positive and negative directions. So that's why it's not necessary, I think, to consider them as separate directions. Whenever slip will happen in both the directions. How two metals are insoluble when they are different crystal structure. Well, they are not necessarily insoluble, but there will be a solubility limit. There will be a solubility limit. So, for example, brass is a very good example. Alpha brass is a solid solution, and alpha brass can take about up to 30% or so, 38% zinc in copper. So 38% zinc can dissolve in copper to give you alpha brass. So it's and copper is FCC and zinc is HCP. The crystal structure are different, but 30 to 40% can dissolve in it. Beyond that, there is a solubility limit. And sometimes the solubility limit is very much limited also. There are examples of that also. But if the crystal structure is different, if you are referring to Hume-Rothery rule, if the crystal structure is different, then complete salt solubility is not possible. Some upper limit on solubility has to exist if the crystal structure is different. That's what is Hume-Rothery's rule, the structure factor. Vinayak Kamath, hello. Ankit Sinha, why does iron have BCC structure at lower temperature and FCC structure at higher temperature? A very, very, very difficult question to answer. Means I don't really have an answer to the question. This is nature's design. This is nature's design. We see it experimentally, and we just accept. Now, one explanation sometimes which can be provided, the thermodynamic explanation, that the structure which will be stable is the one which will have lowest free energy. So that's an obvious answer. And if that satisfies you, or if satisfies your examiners, or whoever you want to tell, that's a good answer to give. That at lower temperature, BCC has the lower free energy, and at higher temperature, FCC has the lower free energy. So at higher temperature, FCC phase is stable, and at lower temperature, BCC phase is stable. However, this is just shifting the question, because then one can still ask, why does BCC phase have lower free energy at lower temperature? And then it is at that point when the question becomes difficult to answer. It's not so easy to show it. But finally, one means at the most fundamental level, one should be able to do the quantum mechanical calculations based on the bond energies and the wave functions of atoms, and should be able to show that yes, the BCC structure has the lowest free energy, and that's why it is stable. But we don't go to that sort of level, and I'm not sure whether that sort of analysis is always possible in each case. And whether it has been done for iron, I don't know particularly whether it has been done for iron to show that yes, BCC iron is the most stable phase. Hope you have answered my question on ammonium chloride. I have already sent you the related file. Vinayak Kamath. I'm sorry, I have not got the files, and I don't know what your question on ammonium chloride is. But let us keep going now. Keep going now. Abbas, hello sir. How difficult will be the certificate exam? See, this is a useful question which worries all students. So it will not be very difficult if you are going through all the weekly quizzes. So we will have questions which will be quite similar to your weekly quiz. You will have some additional questions also. And the format will be exactly the same. It will be usually multiple choice questions. So not very difficult. Don't lose heart. Pratap Sharma, the students of industrial chemistry thinking to go in MSc, will this course be useful? Any students who want to go to MSc, this course is certainly going to be useful, because this is the stepping stone in MSc. Anybody doing material science and engineering, anybody wanting to learn material science and engineering, that's why the name itself says so. It's an introduction to material science and engineering. So if you have not taken a material science and engineering course before, and you want to do a material science and engineering program, or you just want to learn a little bit about material science and engineering, either way, this is a nice course. I mean, I'm not selling my course. Any course of this nature, any introductory course, one introductory course in material science has to be taken if you want to go into material science. Soumyadeep Mondal, material science is included in our syllabus. We are to appear in GATE exam in engineering science. Is there any other way to study material science except the GATE exam? Could you get to what is being asked, Soumyadeep? I'm not very. I've not got your question. Let me think about, or you can reframe your question a little bit. Can you go down? Saik Ismail, Basha, hello. How to examine crystal structure of solids? We didn't get that either. If your intention is to ask how to find the crystal structure or how to determine the crystal structure, the technique is X-ray diffraction, the most important technique, and the technique which we did a little bit in this course. But beyond that, there are techniques of electron diffraction, neutron diffraction. Mostly diffraction-based techniques are the ones which are used to determine the crystal structure. Ankit Sinha, what are dispersoids? Disperoids. I don't know. What are disperoids? Okay. This is what? Okay. So you can now take up the questions which are there. In fact, I had made a note, but I remember one question was, yeah, many of you are asking for assignment solutions, a genuine request. We are a little lax in supplying that to you. So we will be working hard and will provide you all the solutions as early as possible. So this week we should complete the past. But there were a few questions which we have not answered, I think. Yeah, how to gain knowledge of ceramic and glass lining technology? I don't know. This is not my expertise, and I don't know much about glass lining technology. Yeah, there are some questions on dislocations which I can address. Please explain clearly why Burgess vector remains constant at slip region on slip plane and dislocation line. That I can explain. I have done it in the lecture, but since the question is here, I can explain it here also in a live session. Yeah. So essentially we have a slip plane. So let us say that this is the slip plane. And we say that dislocation, so slip is happening on this plane. However, we say that the entire plane slip is not happening. So you can imagine this plane, this rectangle which I have made. You can imagine that this rectangle is cutting a crystal into two halves. One half is behind the rectangle and one half is in front of the rectangle. And this rectangle is now acting as a slip plane. So the front half of the crystal will slide with respect to the back half. But that sliding is not over the entire plane, but is limited over some region of the plane. And let me draw a curved line. Let me draw a curved line to show, divide this plane into two regions, and I write one side and I write one slip and no slip. Why I'm writing this? Because I want to now make this line the dislocation line. And my definition of dislocation line is boundary between slip and no slip regions. So by this qualification, this line becomes a dislocation line. Slip has now happened only on this side. There is a slip side. And there is no slip happening on the other side of the boundary. So this becomes a dislocation line. And dislocation line is changing direction, we can see. So the tangent vector, unit vector tangent to the dislocation line, is called the tangent vector E, and that you can see is changing direction. But what is Burgess vector? The Burgess vector is let me use red for Burgess vector. So the Burgess vector for the same dislocation line is the magnitude and direction of the slip. When I say this was slip and this was no slip region, so the slip side must have slipped by some vector. Let me say that that slipping vector is this. So this is the vector which gives the magnitude and direction of the slip associated with this dislocation line. And that's why, since this entire dislocation line is this entire region of slip has the same slip, same Burgess vector. So the dislocation line also will be said to have the same Burgess vector, which is the magnitude and direction of the slip. This is a way to see why Burgess vector should remain constant. I think same student had also asked why dislocation line cannot end abruptly. So maybe we can answer that also. This is also Pratap Sharma. So Pratap, answering Pratap Sharma's other question. His other question is it true for edge dislocation? Sorry, dislocations cannot end abruptly inside a crystal. Now he has a doubt that whether this statement is true only for edge dislocation or also for screw dislocation. And he says that there is an abrupt end of dislocation in a crystal for a screw dislocation. Actually, it's true for both. Can I get a new page on this? How to get that? So the fact that dislocation cannot end abruptly inside a crystal is true for edge or screw or mixed, any kind of dislocation. Because the whole idea of not ending abruptly is linked with the fact that this is a boundary between slip and no slip region. So if I want to have a boundary between a slip and a no slip region, and a dislocation line is ending abruptly like this inside the crystal, then it does not really qualify as a boundary. Will you call this a boundary between slip and no slip region if it is ending like this? Because you can now walk from the slip region to the no slip region without crossing the boundaries. And the whole idea of having two regions with a boundary should be that from one region you can't go to the other region unless and until you cross the boundary. So then this line does not qualify as the boundary between slip and no slip region, and these regions do not qualify as two different regions. So to have two different slip and no slip region and to have a boundary between them, it requires that the dislocation line is continuous from surface to surface in this case. But of course, as we have seen in the lecture, if there are other grain boundaries or other dislocations, it can end on those also or can form a loop. Thank you. How to, yeah, so we can answer this question. Yeah, so a question by Mahi Kumar Upadhyay is how to find the number of atom present in iron atom if you plane in iron atom if you plane is given like, so I think what you are trying to say that how to find the number of atoms per unit area on a given plane in iron or in any other crystal. So let us consider the BCC iron. So we have atoms at corners, an atom at body center. And now if we have a plane, let us say this is our X, Y, and Z axis. So I have a BCC unit cell with X, Y, and Z axes, and I have drawn this black plane, and you can clearly see that the Miller indices of this black plane, it intercepts X axis at 1 unit, Y axis also at 1 unit, and is parallel to the Z axis. So the Miller indices is 1, 0, 0. Now I need to find out, if I want to find the number of atoms per unit area on this plane, then I have to find what atoms are lying on this plane. And by definition, of course, you can think of that atoms are large and they may be intersecting the plane or so. But by definition, we consider only those atoms to be lying on the plane if their center is lying on the plane. If that is my definition of lying in the plane, then you can see that these 4 corner atoms will be lying in the plane and the center atom will be lying on the plane. And then the question is, how many atoms per unit area? So you can see that the 5 atoms are within this rectangle, and rectangle has a certain area. However, we cannot count all these 5 atoms belonging to this rectangle, because you can see that when you continue this plane, 110 plane is not just this rectangle. 110 plane is that entire plane which is defined by that rectangle. So if you look in this way, then you can see that each corner atom, this one for example, is belonging to actually 1, 2, 3, 4 such rectangles. So we will take only 1/4 of this atom as belonging to 1/4 of this atom belonging to this rectangle. Similarly, 1/4 from each of the corners. By this effective number of atoms from the corner belonging to this rectangle is just 1/4 from each corner, or 1/4 times 4 is 2. Sorry, 1/4 times 4 is 1 from corner. And there is 1 in the center. So we have +1 from the center. This is corner. This is center. Oh, I've lost. Can I get my screen back? Yeah, thanks. So, and so there are 2 atoms. And if you look at the area, this is face diagonal. So this is root 2a. And this is height. So this is a. So the area is root 2a square. Area is root 2a square. So number of atoms per unit area is 2 divided by root 2a square, or root 2 by a square. This is the analysis you have to do for whatever plane which you want to get the number atomic density. I hope I have made it clear. Different lattice parameters of different crystals resist the 2 bodies to merge in one lattice parameter, which result when solid solution forms. Is the solid solution forms? Yes, what you are saying is right. So the two elements which are dissolving in one another, in their pure elemental form, they will have different crystal they will have different lattice parameter, but they will form solution. The lattice parameter will be some sort of average lattice parameter between those two. This variation, in fact, the lattice parameter variation, for example, can I get this? So in fact, if you have, let us say we are mixing 2 elements A and B. So we have weight % B going from 0 to 100, and we have lattice, and let us say that both are of the same crystal structure. So both are monatomic FCC, and let me say that the lattice parameter of A is AA, and lattice parameter of B is AB. Then the lattice parameter of any solid solution which you will make will have some value, and the variation need not be exactly linear. So variation need not be exactly linear. Linear variation has actually a name. This is called Vegard's law. We have not discussed this in this course, but this linear variation is known as Vegard's law. However, the variation which actually may happen maybe something like this, let us say. So we will call it a positive deviation from Vegard's law. Or it may be like this. Then we will say it's a negative deviation from Vegard's law, and so on. So the lattice parameter adjusts. Amrit. Sir, why we use cementite in iron carbon equilibrium diagram, apart from the fact that it is metastable and get decomposed into ferrite and graphite? So that's an interesting question. So the metastability, see, we live with metastability. We cannot demand equilibrium all the time. And when we say metastable, although technically it is metastable, it does not mean that it will immediately decompose into graphite and iron. So cementite, although metastable, remains as cementite in all our steel structure for a very long time. So for practical purposes, it is still a stable structure. From engineering point of view, it is stable. From thermodynamic point of view, it is not stable. Think of diamond. Diamond is an unstable phase. So you don't want to, you should not put money in diamond. Diamond is not forever, despite the advertisement. So the stable phase for carbon is graphite. So diamond over time should convert into graphite. But it does not happen in our lifetime, and we are happy accumulating diamond. Sir, will this course be useful for bark interview? Now I don't really know what you have met anybody who has faced bark interview. If you can tell me what kind of question they ask, then I can tell you whether the course is used. If they are going to ask basic material science questions, then the course will definitely be useful. If they are not asking basic material science questions, then it has no relevance to the interview. So I have never been in bark interview panel, or I have never talked to people who take such interview, or talked to any student who has given such interview. So I really don't know what is involved in bark's interview. So sorry, I am not capable of answering your question. Vinayak Kamath. In atomic solids, atomic centers lie at lattice points. How about molecular solids? What exactly sits at lattice point? Center of gravity of molecule? It's a good question. Let me do it with a drawing. Let me make a two-dimensional atomic solid. As you have seen from my lecture, I am better in drawing on paper. On computer, I am not so used to. But you can think of it as a square crystal where the atoms are on the corners of a square lattice. So this is the crystal. Now the question is whether the atoms are sitting on the lattice point or not. Really, it is my choice that whether I want my lattice point to coincide with the center of atoms or not. Okay, so even in this case, it is not immediately obvious that atoms are sitting at the lattice point. So for example, one choice of lattice points will be the center of atoms. And I can be happy with that. And I'll say this is a square lattice with one atom sitting at each lattice point. So I have a square lattice with one atom motif, one atom at 0, 0, 0. But just for the sake of argument, I can select my lattice point as the centers of the square. Instead of corner of the square, I can select my lattice point in the center of the square. And I say that this is my lattice for the structure. And I'll not be wrong. Yes, there is a periodic set of points associated with the same crystal. So it's the same lattice. Actually, it's the same lattice. Each lattice point you can see is shifted from the previous set of lattice points by the same vector. But now I will describe the same crystal as a square lattice, again with one atom motif. But now it's not at 0, 0, 0, it is at half half. The one atom which is sitting is at half half 0. So I will say that in this monatomic elemental structure, but atoms not sitting at the lattice point. Now you can see that this I am making for an argument's sake. Nobody will really like to do this. One will be happy with this. So now coming to your second part of the question, that what happens if I have a molecular solid? So let me try to get a molecular solid. So let me try to draw an AB compound. So I have an element A. And I have an element B. So this AB molecule, now AB molecule is repeating periodically. Where do I select my lattice point? Now I have two obvious choices. Either I select at the center of A, but then B will not be at the lattice point, or I can select my lattice point at the center of B. Then A will not be at the lattice point. Or as you suggested, we can select somewhere in the middle at the center of the gravity, where neither of them is at the lattice point. So in fact, crystallographers have certain rules. They prefer certain symmetric sites to choose their lattice points. But there is no hard and fast rule. You are really more or less free where you select your lattice point. Please provide the answer of the question homework in the lecture of carbon nanotube. What was that?
We'll be giving all the solutions.
Yeah, but what was that question which he wants?
One more question. You were asked to express D in terms of the length of spiral vector in terms of lattice parameter.
Well, I'm sorry, I have forgotten the question. So anyway, we will upload the answer to your questions.
Wasn't an assignment question. This is some question.
Okay. In the lecture.
Yeah. After all the NN notation. Yes. Just the length.
See, that is I don't know. Okay, let us do that. Now, Shrikant is telling me that the question was probably to relate the length of the chiral vector. Let me try to make hexagonal graphene. So this is a few hexagons shown, and you select a basis vector which is at 60 degree, and note that alternate carbon atoms are equivalent, not the nearest ones. Okay, homework exercise. What is that homework? Both diameter d and chiral angle theta of an NMCNT can be expressed in terms of n and m. Yeah. So if you have any this will be the next equivalent. So suppose you have, oh, what did I select?
That's more.
So suppose this is your CNM. So which means that you take you go n times A1 and you go m times A2. And you know that this angle will be 60 degrees, so this will be 120 degrees. So now you know you have to just solve a triangle whose sides are n times A1, m times A2. A1, A2 you know. So you can solve the third, and the angle you know. So using trigonometry or geometry, whatever you feel like, you can solve for this length and you will get it in terms of n and m. And similarly, you can solve this angle, which is the chirality angle. I don't want to do this exercise here on the screen for you, but I think it should be possible for you to do it. I I will take them as synonymous. Iron carbon equilibrium diagram or iron carbon phase diagram. I will take them as synonymous. Although, if you are insisting maybe on the fact that if Fe3C is not stable, why are you calling it iron carbon equilibrium diagram? So it is iron carbon metastable equilibrium diagram or iron carbon metastable phase diagram. One can one can say that, but in common practice, it's quite common, and both are used equivalent. What is a Eutectoid system? Yes, it's coming in the next week's work, but since you are asking in advance, if you know eutectic, in the eutectic transformation, if I can write, and there's a lot of discussion on iron carbon already, so we can take. So in the iron carbon system, you have the eutectoid reaction, where gamma iron, if you cool, around 725 degrees Celsius, and let us say gamma is of 0.8% carbon. So on cooling, it undergoes a transformation, and that transformation is to a solid phase alpha, which is more or less pure iron, 0.02% carbon. It has very less carbon. This is BCC, this is FCC, and the compound Fe3C. So this reaction, this transformation on cooling of one solid phase, this is an example, not necessarily an eutectoid reaction is a generic reaction. So many reactions are eutectoid reactions. This is an example of eutectoid reaction. Any reaction in which cooling a single solid phase gives you a mixture of two solid phases. Any reaction in which a cooling of a single solid phase gives you a mixture of two different solid phases, that is called a eutectoid reaction. So in the case of steel, it's the austenite gamma, which changes into ferrite alpha plus cementite Fe3C. This eutectoid reaction specifically for steel has a special name also, pearlitic reaction, because this mixture alpha plus Fe3C is called pearlite. Sheikh Ismail, sir, is there any chance of one element has more than one crystal structure at the same temperature? It can if the temperature is the transformation, equilibrium transformation temperature. So, for example, again, keeping yourself the example of iron, if you have iron, and this is, let us say, the temperature axis. So you have 910 degrees Celsius. Above 910 degrees Celsius, gamma or FCC is stable. Below 910, BCC, alpha is stable. At 910, both are stable. They are coexisting. So you can have both alpha and gamma, BCC and FCC at the same temperature, but then you have to be at 910 degrees Celsius. It's just like, it's the same as your water, that you can have ice as well as water at the same temperature, but then that temperature has to be 0 degrees Celsius. This is an interesting question. That why a maximum of 6.67% carbon only is considered in the iron carbon diagram. I really don't know the answer to this. 6.67% is the composition of Fe3C. Obviously, some phases will exist beyond 6.67% as we go towards more and more carbon. But one reason can be given that mm, anything beyond that is probably not of practical interest, because already by Fe3C we are into a very, very brittle regime, and it's a very brittle material. But I don't see scientifically any good reason. There should, for sake of scientific curiosity, we could have a study beyond 6.67. But I have also not come across this phase diagram beyond 6.67, and I don't have a good reason to justify that why we have nothing beyond 6.67. But possibility is there. One can have it. What is the difference between phase diagram and equilibrium diagram? Not, I will consider them to be equivalent phrases. On what topic we should focus for GATE, as it has limited topic given in their syllabus? I don't know. I can't answer such questions because only your GATE coach or somebody can tell, because I am not familiar with the GATE syllabus and the patterns of asking questions. So I really cannot guide you on this. Chandan Kumar. Sir, how the plane normal to the closed packed plane in HCP crystal is along the six-fold axis of the crystal?
Yes, I mean,
Hmm?
the answer. No.
So we can answer now, but what? Let me understand the question. That how the plane normal to the closed packed plane in an HCP crystal is along the six-fold axis. I don't know whether the worry is that that axis is not a six-fold, or hmm, what is the question? The plane normal to the closed packed plane in HCP crystal is along dash of the crystal. Okay, six-fold axis of the crystal. So I think uh, we thought that it's not a very difficult question, but if you are facing difficulty, I'm happy to spend some time on it. So you have the HCP crystal. So this is my HCP unit cell, and this is my closed packed plane. This is a closed packed plane. So you can see both, and of course, I'm missing 3 atoms inside. There are 3 atoms inside. So these planes are closed packed planes. Closed pack, because although I have drawn here in a blown out form, really the central atom is touching all the 6 surrounding atoms. These 7 atoms shown on the top is really in a hexagonal arrangement like this. So this is the closed packed plane. So the closed packed plane in this diagram, you can see that the closed packed planes are the horizontal planes. And the normal to that will obviously be the vertical direction. So normal to these closed packed planes is this direction. And this in the hexagonal crystal is the six-fold axis. So the closed packed planes are the horizontal plane. The normal is the vertical direction. and that normal is a six-fold axis of the hexagonal crystal. I hope I have answered your question. If you still have doubt, you can shoot more questions. Electrical engineering, yeah, electrical engineering, a lot of material science is there, and in fact, one of the faster advancing areas of material science is electrical and electronic materials. So electronic materials, functional materials, semiconductors, semiconductor technology is very much material science, is governed by material science and materials development. A lot of material scientists now are working in electrical and electronic materials. So it has a very good scope, I would say.
Sounds good.
So I think we have answered all your questions, and our time is also interaction time is up. So thank you. Thank you for. Hmm? There. Okay, let me address that. Mm, but I only have to give an excuse. So there is a question by whom?
Boss.
Abbas has asked a good question, an interesting question, that why, according to you, what according to you is the scope of polymers in the future? Well, I'm not an expert who can tell the future of various fields, but yes, polymers are an important class of material and has a very good future, I'll say. And it has already become an indispensable part of our life. We cannot live without polymer. But then also it has associated environmental problems, which any other material also has other associated environmental problems. So environmental problems of production as well as of disposal, all these challenges will be there for future. So material scientists with other scientists have to handle these problems and solve them. So definitely it has a lot of future. Your second question, I'm not an expert. I have to accept my ignorance. That why is Bucky paper so expensive? Can we synthesize it in an ordinary lab? So I'm not aware what is the answer to this question. So thank you. Thank you very much for all your questions. Thank you for spending time. If enough demand is there, we will meet again in the course and keep what I have know, what I am little concerned about and little worried about is that there is not enough day-to-day discussion on the forum. So please shoot questions. Don't wait for the next live session to ask me the question. Please shoot questions on the forum also. Forum questions also is seen by me and my TA Shrikant, who is a great help to me. Shrikant, thank you very much. And so he and me, both of us see the question. Both of us many times discuss among ourselves before answering the question, and so on. So we give a lot of weight, a lot of respect to the questions which you are asking. And if the questions are not coming, we start getting worried. Just like in my live class, if the students are just sitting dumb and not asking any question, I'm worried that whether my lecture is going through well or not. So every teacher wants his class to be lively, and every teacher wants questions to be thrown back to him. Same with Mo. Although here person-to-person contact is not possible, but I do want you to look at the videos and whatever difficulty you face while looking at the video and while trying to answer the question, you do shoot questions and we will try to answer to the best of our capability. Thank you.